to inject quantum mechanics into our understanding of things like black holes, and that's where Hawking proved that black holes are not completely black. Astrophysics, the branch of science that seeks to understand the universe and the way it works, has long been interested in the mysterious concept of black holes. Black holes are regions in space with such immense gravitational pull that nothing, not even light, can escape from them. Their existence was first theorized through Einstein's theory of general relativity in the early 20th century, and over the years, extensive research and observations have reinforced their significance in our understanding of the cosmos. One of the tools researchers use to figure out the realities of space is the James Webb Space Telescope. While it wasn't meant to study black holes, since the focus is on the entirety of observable space, it's bound to pick up information about black holes too. But the problem is, the information it's picked up is the exact opposite of what we were expecting. Brian Greene has just confirmed the recent finding, and it turns out, according to the James Webb Space Telescope, black holes aren't real. Join us as we bring you all the details. Telescopic imagery from the Event Horizon Telescope of the black hole in M87, which ripped on the fabric of space, was the most direct evidence about this shocking discovery and how it's turned the world of science upside down. Black holes are cosmic entities predicted by Albert Einstein's theory of general relativity. According to this theory, massive objects form the entire fabric of spacetime, creating what we perceive as gravity. When a star runs out of its nuclear fuel and undergoes a supernova explosion, its core collapses under the sheer force of gravity. If the remaining mass exceeds a critical limit known as the Chandrasekhar limit, the gravitational collapse becomes irreversible, leading to the formation of a black hole. But even with that, black holes have always been theorized about since their initial discovery. While black holes themselves can't be directly observed because of the way they're created, scientists have identified several key characteristics and properties through indirect observations. As light from background stars or galaxies passes near a black hole, its path is bent by immeasurable gravity, creating a gravitational lensing effect. While it sounds absolutely trippy, it's the only thing that allows astronomers to detect and study black holes indirectly by actually studying their gravitational influence on surrounding objects. So what's around the black hole is very important here. When matter from nearby stars or gas clouds falls toward a black hole, it forms an accretion disk around the black hole. These vibrations, created by the black hole, ripple through the gas cloud. These vibrations are then picked up on planet Earth, massaged by a computer, and amplified by 57 octaves. The material in the disk becomes superheated and emits X-rays, providing another observable signature of black holes. The vision or interaction of black holes with other massive objects can produce gravitational waves, ripples in spacetime, which were directly detected for the first time in 2015. So there are both very old and new observations that have been made over time. Over the decades, extensive astronomical observations and advances in technology have provided quite compelling evidence supporting the existence of black holes. Gravitational lensing has offered a look into the distorted light from background objects, indicating the presence of massive objects with intense gravitational fields. Plus, X-ray emissions from accretion disks around invisible objects have matched theoretical predictions for black holes. Not only that, but the detection of gravitational waves, specifically from the merger of black holes, has provided direct confirmation of these powerful entities. The James Webb Space Telescope is a technological marvel that was created to revolutionize astrophysics, and it has not disappointed in its mission to uncover the secrets of the cosmos. As researchers eagerly waited for its data, they were not prepared for the astounding revelations it would bring. Armed with this state-of-the-art observatory, scientists went on a journey that led them to make extraordinary claims that challenged the very existence of black holes. Yes, researchers utilizing just data have reported intriguing phenomena that appear inconsistent with our traditional understanding of black holes. Some of these findings have pointed to the possibility of alternative explanations for the things we always thought were proof of black holes. And well, let's just say that the world of space exploration has done a complete 180. One of the problems has to do with gravitational lensing. With the JWST's advanced observational capabilities, researchers were expected to witness familiar gravitational lensing patterns that align with our understanding of black holes. The light should bend, and there should be that big black hole of nothingness that's causing light to distort. However, some of the observed gravitational lensing events presented strange results. You know, when matter falls toward a black hole and forms an accretion disk around it, the superheated material emits X-rays, which are detectable by telescopes. These X-ray emissions are among the key observable signatures used to identify black holes and study their properties. If the black hole's mass goes up by the amount of mass that falls in, even that concept is being turned around on its head with the JWST. Scientists have scrutinized regions suspected to contain black holes, observing their X-ray emissions in greater detail. Unexpectedly, certain black hole candidates have shown peculiar patterns in their X-ray emissions that challenge the conventional understanding of these cosmic entities. The expected variations in X-ray brightness, spectral characteristics, or timing properties have left researchers wondering if traditional black hole models adequately account for these emissions. This uncertainty has given rise to alternative explanations that explore the possibility of other exotic compact objects or modified gravity theories. One of these has to do with gravitas. These hypothetical objects have captured the imagination of astrophysicists as they present a unique twist on the classic black hole theory. In the gravity model, the exterior still appears similar to a black hole, following the well-known metric that describes gravity's behavior around such massive objects. However, a fascinating twist lies within its core. Instead of a singularity like the one postulated in traditional black holes, gravitas have more of a distinct metric inside. What takes things even further is its event horizon, which hosts a thin shell of matter. This peculiar configuration sets gravitas apart from conventional black holes and prompts scientists to consider intriguing possibilities. The Laser Interferometer Gravitational Wave Observatory, LIGO, has also played a pivotal role in our overall journey to explore the cosmos. Detecting gravitational waves from distant cosmic collisions has allowed LIGO to provide valuable insights into the nature of compact objects. Plus, in some instances, the gravitational waves detected by LIGO have also exhibited characteristics that are completely indistinguishable from those of ordinary black holes. So, something is going on here in the realm of astrophysics and general relativity. The no-hair theorem has long stood as a prominent principle shaping our understanding of black holes. According to this theorem, all stationary black hole solutions to the Einstein-Maxwell equations, which describe the gravitational and electromagnetic forces, possess a unique set of characteristics. These specific attributes are the black hole's mass, angular momentum or spin, and electric charge. Collectively referred to as the black hole's hair, the no-hair theorem suggests that any other distinguishing features of a black hole, beyond its mass, spin, and charge, are considered hair and are believed to be lost beyond the event horizon. This event horizon acts as an impenetrable boundary, beyond which information is seemingly irretrievable from an external observer's perspective. So, to put it in one sentence, conventional black holes have been thought of as relatively simple and devoid of any further distinguishing properties. However, in a remarkable study, Sasha Hako, Stephen Hawking, Malcolm Perry, and Andrew Strominger challenged this traditional view of black holes. Their groundbreaking research presents the existence of what they call soft hair in black holes, suggesting a more complex structure than anyone previously thought. Soft hair refers to a collection of quantum properties that are thought to reside on the black hole's event horizon. Unlike conventional hair, soft hair is not associated with the black hole's mass, spin, or electric charge. Instead, it is believed to have subtle quantum properties that encode information about the black hole's interactions with its surrounding environment. The existence of soft hair would have profound implications for our understanding of black holes and the nature of information in the universe. It could potentially resolve long-standing questions related to the information paradox, concerning what happens to the information of matter that falls into a black hole. The idea of soft hair hints at the possibility that black holes may retain subtle quantum fingerprints of their past interactions, raising the exciting prospect of retrieving information that was once thought lost beyond the event horizon. And if that's true, then what the James Webb Space Telescope found would be true too. But if you reel things back in time a little bit, this concept has actually been around for a really long time. Back in 1974, Stephen Hawking proposed a groundbreaking idea called Hawking radiation. According to this, black holes emit radiation over time, which causes them to lose mass and eventually disappear. At the time, though, this radiation seemed to be random and didn't carry any information about what fell into the black hole, which clashed with the principle of information preservation in quantum theory. Scientists did try to combine quantum theory with gravity to solve this paradox, but they ran into mathematical problems and couldn't make sense of it. The situation seemed quite confusing, which is probably why the theory didn't actually pick up and somewhat disappeared as the world of science went on, however. A recent study led by Netta Engelhardt and her team made exciting progress. They re-examined Hawking's formula and found a new calculation suggesting that information does escape black holes through their radiation. After all, the revised formula proposes that the radiation carries subtle traces of the lost information inside the black holes. As the black holes evaporate, they emit this radiation, revealing some details about the matter that had fallen into them. This discovery is a significant step forward in understanding the ultimate fate of information that falls into a black hole and may provide the key to resolving the long-standing information paradox. The mystery of black holes is far from over, and our understanding of them continues to evolve. With the help of powerful tools like the James Webb Space Telescope, we are constantly uncovering new information that forces us to rethink some of our most basic assumptions about the cosmos. Whether or not black holes as we once imagined them truly exist may remain up for debate, but one thing is certain. Our quest to understand the universe is far from over, and we are getting closer to unlocking the greatest mysteries of the cosmos, as new data from the James Webb Space Telescope, JWST, continues to challenge conventional black hole theories. It's becoming clear that our understanding of these cosmic objects may require significant re-evaluation. While the telescope's observations have provided stunning images and insights into the distant universe, some of its findings contradict previously held assumptions about black holes and their behavior. For example, JWST's high-resolution infrared capabilities have allowed astronomers to closely observe distant galaxies and their core regions, where supermassive black holes were once thought to reside. However, some of these galaxies appear to lack the expected signatures of supermassive black holes, such as high-energy X-ray emissions or intense gravitational lensing effects. Instead, the data suggests the possibility that these regions could be home to entirely new types of compact objects, which might not fit into our traditional black hole models at all. In some cases, researchers have observed mysterious objects with immense gravitational influence that do not exhibit the classical characteristics of black holes. These objects may be part of a new class of phenomena that defy the established physics of general relativity, such as extremely dense stellar remnants or even exotic matter configurations. If these objects indeed exist, they would significantly alter our understanding of how gravity behaves in the extreme environments near the centers of galaxies. Moreover, the search for alternative explanations to black hole-like phenomena has led to a re-examination of some of the most fundamental principles of physics. Theories such as modified gravity or quantum gravity have gained traction as possible ways to account for these unexpected observations. Modified gravity theories suggest that the force of gravity might behave differently on galactic scales than predicted by Einstein's general relativity, which could explain the strange behaviors seen around these mysterious objects. Quantum gravity models, on the other hand, seek to reconcile quantum mechanics and general relativity and may offer insights into how space-time behaves under extreme conditions. Additionally, the recent confirmation of gravitational wave events by LIGO, Laser Interferometer Gravitational Wave Observatory, has added another layer of complexity to the discussion. The detection of gravitational waves from binary black hole mergers has traditionally been interpreted as proof of the existence of black holes, yet some researchers have questioned whether the signals could also be explained by other exotic objects, such as boson stars or gravastars. These potential alternatives challenge the very foundations of black hole theory and suggest that the nature of compact objects in the universe may be far more varied than we once imagined. Ultimately, the ongoing revolution in our understanding of black holes is forcing scientists to rethink the boundaries of modern physics. Whether the traditional view of black holes will hold or whether new theories will emerge to replace it remains an open question. What's clear is that we are entering a new era of discovery in which the universe's most mysterious objects are once again proving to be far more complex and far more elusive than we ever anticipated. As the James Webb Space Telescope, JWST, continues to refine our view of the cosmos, researchers are increasingly finding that the mysteries surrounding black holes may be deeper than we ever realized. While the JWST was designed to observe distant galaxies, stars, and nebulae, its findings have inadvertently prompted a reassessment of the very concept of a black hole. Some scientists now speculate that what we once thought were black holes might instead be manifestations of other exotic phenomena that have not yet been fully understood. The idea that dark matter and dark energy could play a role in the formation of cosmic objects similar to black holes is gaining traction. Dark matter, with its unseen mass and gravitational effects, could potentially explain some of the phenomena traditionally attributed to black holes, especially in cases where the expected X-ray emissions and other signatures are absent. Similarly, dark energy, which drives the accelerated expansion of the universe, might exert gravitational effects that mimic the intense pull of black holes in certain regions. As we push the boundaries of technology and theory, the quest for understanding the most extreme objects in the universe will continue to challenge and expand our knowledge. The true nature of black holes, whether they exist in the form we've always envisioned or something entirely different, remains one of the greatest unsolved puzzles in astrophysics.